Today's topic is distributed systems. Distributed systems is an absolutely giant topic, but thankfully we only really care about a small corner of it. The things that we want are to create reliable, robust, persistent systems, and that allows us to avoid a couple of corners about distributed systems that are, well, introduce complications that we don't really care about. So the thing we want is reliability, and one of the things we get, or one of the ways we get reliability is by distributing our system. So instead of having one elevator, we have 3 elevators, for example, as a very simple form of distribution. You've already been through these classic failure modes: the failure in computation, failure in storage, failure in communication. 2 of these things you get quite easily from physical distribution. Failure in computation, have more computers. In our project's case, more elevators. Failure in storage will have more places where you store your orders so you don't lose them. In this case, multiple elevators, or you can have it on disk or disks or so on. Communication, well, communication is a bit more weird because you can't really just spread your communication on multiple communications. Unless you have multiple channels of communication, of course. So you have network and wireless and people walking with physical letters. That's one kind of distribution in communication, but it doesn't really make a whole lot of sense. And besides, the way we solve our distribution in computation and our distribution in storage is with communication. So communication itself, not really a distributable thing. It's used for the distribution of other things, but communication is still unreliable. So how do we deal with this? How do we make unreliable, or how do we make reliable communication from unreliable communication? So let's look at the ways communication can be unreliable, just to refresh our memories here. The classic thing is lost messages. You can think of this as the message doesn't happen. So if we're trying to send something to another node, we can think of this as the time doesn't occur. The time for this message, or the time contained in this message, does not occur. And then the messages can be reordered. So the time the message arrives at, or the time contained in the message, is happening in the wrong order. Or we can have duplicated messages if we're trying to resend, because if you have a lost message, the most obvious thing to do would be to resend it. And in that case, time would be happening more than one time. Really, you can think of this message reordering and message loss phenomena as we need to think about how the timing of our received messages happens. The thing is that the messages that we receive are the basis for the computation that we do. So for a classic state machine, if you were to make the calculations of what the state machine should do on one node, and then the execution of the state machine on the other node, if you lose that communication, the state machine that is actually, or the thing that is executing the orders, will be doing something wrong if messages are lost or reordered. So if we have unreliable communication, we will have an unreliable entire system, and we will have unreliable observable outputs of our system. So what we really need is some way of controlling the flow of time as received by our program. We can't control the flow of time coming out of the other nodes, but we can hopefully control the flow of time coming into our program. That's a different way of thinking about the same problem. These are the same problem, just formulated different ways. Hopefully one of them makes, if one of them doesn't make sense, hopefully the other one does. I don't know if you've been through this before. The cap theorem, have you touched this before? No? Okay. I'm not going to go through the math because who cares? But it states that you can have 2 of the 3 of the following. You can have consistency, availability, and partition tolerance, but only 2 of the 3. If you want 2 of them, you have to give up the other one. Consistency means that all of the nodes agree on the same information. Availability means that if you input something to the system is responsive to your inputs. And partition tolerance means that if you lose a node, the system will continue operating the way it should operate, for some definition of should operate. So let's just look at the intuition here. If we want availability and partition tolerance, everything needs to work all the time, and we need to work even if we don't have everyone here. In that case, we just have to go even if we don't have everyone. If we don't have everyone, we don't know what they know, so we lose consistency. If we want consistency and availability, everybody agrees and it's always responsive. Well, then in that case, if we lose a node, we would lose consistency, or if we have to wait for them, we would lose availability. So in this case, we can't tolerate losing a node, even temporarily. And then if you want partition tolerance and consistency, so everybody agrees and everybody stays together, well, in that case, you would have to wait in case you lose a node. If you lose someone, you have to wait for them. Hopefully this is enough to just build a general intuition that you can't have a perfectly consistent, full uptime system that also is tolerant to losing nodes. It should make sense. You can't have uptime and lose everybody and everybody agrees all at the same time. That doesn't work. Here's how we apply it to the project. And this is where we start narrowing down the domain of distributed systems to the things that we care about. We need availability and partition tolerance. If we push a button, it needs to work. If we lose a node, it needs to continue working. So since we need these two all the time, the one that we need to mess with is consistency. So full uptime, full availability, full partition tolerance, let's mess with consistency. And you already have an intuition for this, I think. There's some inconsistent behavior that we have already intuited that we are okay with losing. For example, the button light doesn't turn on, but an elevator moves. Who has that in their design? Is it something that shows up? None of you? Kind of-ish? Multiple elevators respond to the same call. It's an easable, yeah, exactly, that one showed up. And restarting, but you don't know what's there. Well, or you have to read from other nodes or read from disk or something like that when you're restarting. Yeah, makes sense. So there are these transitional periods where you have inconsistency in the system. And this already makes sense. Now the question is, of course, how do we deal with this consistency? So I've listed up 3 goals here. These are actually all the same goal as far as I can tell. We want solutions to dealing with non-monotonic time. The timing of the messages appearing in not the correct order. And we also need need to allow some minimum amount of inconsistency in our system. From the cap theorem, that's just the way it has to be. And of course, we don't want all of the inconsistency in the entire world. We don't want to give up on consistency entirely, so we want to impose some limits on what we receive, but not impose, well, we can't impose no limits, then we get complete inconsistency, and of course the system won't work. And we can't impose all of the limits because cap theorem. So we need to find what that limit is. Consistency, if it isn't completely clear, it means free from contradiction, or all nodes agree, which is the same thing. It also means free from paradox. There is only one way to get contradiction, and that is by having both negation and self-reference. Think of this in terms of paradoxes. How many paradoxes can you think of that don't have self-reference and negation? Classic paradoxes like this sentence is false. This sentence, self-reference, is false, negation. Or the barber's paradox, the barber is the one who shaves everyone who doesn't shave themselves, self-reference, doesn't, negation. So exercise for the reader, try to find a paradox that doesn't have both self-reference and negation. TLDR, you can't. So we want to enforce consistency. So the way we enforce consistency is by removing the ability for the system to utter paradoxes, which means that we need to remove one of these two, either negation or self-reference. Self-reference is somewhat inevitable. The system needs to be able to talk to itself, either directly by looping or indirectly by sending a message to one node, which sends a message back to its node. So you can't get away from self-reference. Cool, now we have only one thing left, which is negation. So we need to limit negation. So we've narrowed down distributed systems to, we need to limit the scope of negation in our communication. And negation in this case means not counting upwards, or not continuing to count in the same direction. Not everyone moving in the same direction, but somebody taking a step back. In this case, resets, reverses, deletes, and so on. Again, I think you already have an intuition for this, which I think is in a slide later, so we'll cover it there. But briefly now, you already noticed that the biggest problem isn't really making sure that everybody knows about an order. That's just everybody tell them that there is an order, and everybody's like, oop, there's an order, I'm going to tell everybody else that there's an order, and so on. The problem occurs that when you try to tell everybody that it's no longer there or it's been completed, that's where it starts getting hairy. So in order to limit negation, we need to limit the kinds of messages that we are willing to receive. In this case, we need these messages that tell us to go back, to reset, to delete, to complete orders, and so on. That thing has to be limited when we accept it. We can't just accept it at any time. Oh yeah, here's the example on this slide. Let's say we have a trivial binary system. No order, it's Boolean 0, and there is an order, it's Boolean 1. If we receive a 1, that means that there is an order, it overwrites our 0. Pretty obvious. And then if we start sending out that we have received the order, then eventually everybody will get a 1, because this is eventually consistent. Since the 1 always overrides a 0, if we have a 0, we override it. If somebody else has a 0 and we send a 1, they override it. Everybody eventually will agree and get to a 1. The question is obviously then, how do we remove orders? Because if we try sending a 0, somebody else is sending a 1 and saying happily, yes, there is an order here. We try to reset ourselves to 0, and they sent a 1, and they're like, yep, there's an order here, and we're like, yep, there's an order here, and we can never delete it. Which means that we can't just accept this 1 at any time. We can't just accept the 0 at any time. There is some amount of ordering here needed to get this to work out correctly. So let's impose some ordering. Let's try an order counter, for example. Try to only override the data if it is newer than what we have. Seems like a reasonable start, I think. But now we start getting more interesting questions like, do these counters need to be in sync? And how do we get them to be in sync? And is it safe to discard all old messages and just accept only the newest one? And of course, I didn't include this one, so I'm just saying it's of course, but it's not really of course. But how do we deal with restarting? If we restarted and our counter is 0 and somebody else's counter is 78, how do we deal with this? Or we restart, our counter is 0, we get a new order, but somebody else's counter is too high so they don't accept it. Or we restart, we complete an order from disk, we communicate that to the network with an ID that is too low, it gets discarded even though it's completed. So it's not just slap a counter on it and we're done. It's a bit more hairy than that, unfortunately. So let's look at when can we discard these messages. Let's look at some extremes, I think. Discard everything that isn't in perfect lockstep. That's pretty extreme. We only accept things if they are in the exact correct order. If they're not in the correct order, we just sit there and wait. Which means that if we lose a message, we're stuck there because we need perfect ordering. Which is incidentally what TCP does. If it doesn't receive a message, it will just wait for everybody and it will ask, hey, can you resend this message? And if it doesn't get it, it will just hang there for a while until it eventually gives up after some defined timeout. I don't know why there's a comma there, but there is. Deal with it. We can also discard all non-monotonic messages, so have this upward counter. If there's something that is newer than what we have, we accept it. If it's a bit newer or completely newer, if we skip a number, fine. This is usually possible, or actually, well, I don't know if it's usually possible, but it's often possible at least. If you just need the latest version of something, that's fine. Video streaming, for example, works this way. If you lose a frame while the video has to continue, there's no point stalling the video to display a frame that was 5 seconds ago. You already skipped it. So who cares? You just need the latest versions. The same applies to real-time games and so on. You can also accept a few downward counting messages. So, for example, a cyclic counter, a single reset. You count to 10 and then you reset back down to 0, for example. In this case, we can accept this reset counter under some condition. The question is, what would that condition be exactly? Well, it can't be that we've reached exactly 10, because if we missed the message that told us to go to 10 and we get the message that tells us to go to 0, how do we deal with this? It's often possible, but you need to be able, in this case, not just to lose a single number, but to lose an entire cycle. So if losing an entire cycle is permissible, you can put in these targeted resets. And you also need to be careful about resetting a node. Well, you need to be careful about a node being reset, because then it will miss out on the entire cycle and it will only catch up the next cycle. And then you also need to be careful about multiple nodes sending the reset at the same time. In case that reset isn't properly defined, then you might reset multiple cycles at the same time. So again, we need to be a bit careful here about exactly when we accept this message. And then finally, on the outer extreme, accept everything. I don't know what kind of counting you would call this. I call it clown counting. We just accept anything at any time. It doesn't matter. Fuck it. Let's just go. Usually not viable. We don't exactly get consistency this way, but if our system doesn't need to be consistent, go ahead. Or if inconsistency and packet loss and so on is so rare that you can just say we don't really care about this in this scenario, go ahead. But if we do need some amount of consistency in our system, then how about no? So we have this unfortunate situation here where a lot of this seems to be quite application dependent. Even though we've narrowed it down to a small area of distributed systems, just find out exactly where we put that reset message. That's all we care about. This question is, well, it's still application dependent. But we do have some guidelines, or I've labeled it solutions, but let's put it as guidelines. Make as much as possible of the system additive. Make as much upward counting as possible. Only have a single reset in a single place. Only add information to the system, don't remove it. It's basically the Streisand effect, but on a small scale. Don't try to remove something from the internet, it doesn't work. You can only add stuff. You can add information that says that the old information is invalid or gone out of date, but you can't remove it completely. It just does not work. If you do need negation, you do need a reset, you do need to count back down to 0, only have it in one place. Don't try to spread it all over. Don't have a counter that can go to either 5 or to 10. Always have it go to the same number. And don't have a downward count and an upward count. Try to have an upward count and a single reset back down to 0. It's much easier. And chances are you will need this, and you will need the reset down to initial state instead of a downward count, because what happens if a node crashes and it restarts? It's been reset. It's not counting down, it's been completely reset. So the reset is probably going to be there anyway. Use it for everything. And on the implementation side, how to choose when to accept and when to discard messages, that's dependent on the data you have already received. So spoilers, the output depends now on the ordering and the history of the inputs. Some combinations of inputs are invalid. I think you've seen this pattern before. You should solve your distributed system problem as a state machine. The transitions are the messages that you receive. The states are the information that you already have. Classic being a straight transition from no order, there is a new order. Okay, there is an order we don't know about. We tell everybody on the system that we know that there is something here, but we don't know who knows about it or that everybody knows about it. You keep counting upwards. Now, eventually you will receive messages from everyone saying that we know about it. Once everybody knows about it, you can transition to the next state. The state where it's confirmed that there is in fact an order that everybody knows about. Now you can turn on the light. Now you can distribute it or execute it depending on the ordering that you've chosen there. Now it's an order that is being executed. Okay, you can keep counting upwards. Now it's an order that's been completed. And you want to go back down to no order. How exactly do you do that? Well, you need a reset message. You only accept the reset message for orders that are confirmed. There's no point in accepting a reset message for an order that is unconfirmed or an order that is not being executed. So in this case, there's only one timing where it makes sense to accept a reset message. That's the TLDR for what your acknowledgement system will likely look like. Right, pattern TLDRs for what have we done for the pattern so far. State machines. How to make state machines. Find all your inputs and outputs. Find the data. Minimize the data. Modularize based on what needs to be modified in sync. Separate by what needs to be modified at the same time. And put everything in, or put these globs of data into their own state machines. If you need to use analytical techniques, chances are you can do a lot of this just by intuition. Once you have the state machine for each thing, divide everything into core and shell. Make as many pure functions as possible. If you are doing modification, do it directly in the state machine. Don't hide it under the carpet of kind of functions. Just put it right there, just be honest. If you're doing modification, just do it in plain sight, don't try to hide it. And then wire everything together with queues and channels. For distributed systems, analyze the specification to find out what kind of inconsistency you are allowed to get away with it. If you do need some amount of inconsistency, and chances are you will, formulate those parts as negations, because you will need self-reference. So find the places in the specification where you need, in the distribution part, where you need the words like not, reset, back, and so on. Those are hints. Formulate all other communication as additive, like up, continue, and so on. If it's additive, then the wrong order doesn't matter. It doesn't matter if you get a reply from A first or if you get a reply from C first. Doesn't make a difference. It doesn't make a difference if you get a reply from A this cycle or if you get it next cycle, if it keeps resending periodically. Doesn't matter. And then formulate the rules for what messages you reject and express that using state machines. Importantly, there is no general solution for distributed systems. And there is no general solution for this particular kind of distributed systems where consistency is the one we're fucking with. It has to be application dependent. There's no avoiding this. So just imagine a forest fire and distributed systems in white text. That's basically distributed systems for you.